Hi, this is Tom Cherryholmes with another video in the Retro Computing Archaeology series. In this video, we're going to be exploring the Trackdisk device on the Commodore Amiga by using it to make a KickStart floppy, using a program that we're going to make here in this video. The Trackdisk device is pretty much like any other device inside the Amiga, serial device, etc., in that it all conforms to a common set of interfaces that programs can use to access various devices inside the system. Trackdisk gives you the ability to use the floppy disk drive in a low-level manner, reading and writing any sector on a particular floppy, and even going lower and altering the device's the floppy's low-level format, etc., etc. But we're going to be using it to make a very special kind of floppy that you normally can't make with typical tools, which is the floppy that is used to boot KickStart on Amiga 1000 computers here. So how are we going to do that? Well, first of all, I'm going to show what we're going to make in the first place. I have my trusty Amiga 1000 workstation over here. We've got our MakeKick ready to go, and we'll come back to you in just a second. But for now, I've opened up another WinUAE window here, and we've configured it as an Amiga 1000 with 256K of chip memory and the Bootstrap ROM. And the Bootstrap ROM, because the Amiga 1000's operating system, the KickStart, was not ready in time for production, it was decided that they would take and make a quick little Bootstrap ROM which had just enough logic in it to take and read the first 23 cylinders off of a floppy and write it into a special section of memory called the Writable Control Store, which would hold the KickStart ROM. Once the data would be loaded into the Writable Control Store, in this case the KickStart image off the floppy, it would take and write protect the Writable Control Store and boot into KickStart. This had the advantage of basically anytime a new version of KickStart would come out from version 1.0 to 1.3, Commodore would release a new KickStart floppy for 1000 users, and they could simply use the KickStart floppy to take and boot the system. However, the downside is that because there's a KickStart floppy and it's not in ROM as intended, Amiga 1000 users have to go through an additional step when they first cold start the machine, putting in the KickStart, letting the KickStart floppy load, then taking and replacing that floppy with the workbench and loading their workbench. Meh. So, with that said, let's see what we're actually going to be doing here. What is a KickStart floppy first and foremost? Well, I've set up a version of configuration of WinUAE as a basic Amiga 1000, and we are going to take and boot it. And yes, I hope you guys heard that. That's a boot chime that's on the original Amiga 1000s, indicating that this is a Bootstrap ROM and that it needs to insert the KickStart. So we'll go ahead, come back into our configuration window here, and insert our disk that we're actually going to be making through the process here. And you'll see right here that it is taking and loading each track sequentially off of the disk, and it is loading it into that special area in memory that will contain the KickStart. This is separate from the memory that's already inside the system, so it doesn't take up your available memory, unlike on the Atari ST, for example. Now it's booted the KickStart, and now it's asking us for the workbench. Well, for this, we're going to take and insert a special one here. Turns out this is a very special version of KickStart. This is version 27, which was the beta that was released shortly before the Lincoln Center performance of the Amiga launch. And there it is right here, version 27.3. The interesting thing about this particular version, there is no workbench. It does not exist. If I go ahead and try to do load WB, there isn't a load WB. If I take and copy it from another disk, it says, well, there's no workbench task. It's just not there. Well, there are other interesting things on this disk. Like, for example, there's the early version of GraphiCraft. And this was the first version. This was the first version of GraphiCraft that was given to Andy Warhol to work with here. He used this to do a lot of demo paintings. The version that was shown at the launch event was further refinement of it, and I did a whole video showing how all of this worked, etc., etc. Okay, never mind. I guess, I'm guessing, it's only got 206K of memory in it, so it can't boot it anyway. My apologies. But you get the point. We're able to take and make a KickStart floppy. We're going to be making this KickStart floppy, and we're going to be booting into it just to show that it actually works. But you can use this to take a KickStart ROM, because the ROMs that we've had for 27.3 have been in ROM format, and not in the KickStart disk image format, because all those disks are long gone, they've been trashed, but we can recreate them. So how do we do that? Well, we're going to use this utility right here to do so, and I'll do a demonstration of this utility. We'll start by going into my system folder, and we'll be going into CLI, and we'll go into this MakeKick directory here. Now, we have our MakeKick tool, and we have a ROM that we're going to put on our KickStart disk. This is exactly 206 kilobytes in length, and this will be written to the disk. If we run the tool by itself, we get a requester with its usage showing basically the parameters that we have to provide, namely the ROM file and the drive that we wish to write it to. Click OK. If we take and give it an improper file, it'll say it can't open the ROM file. Okay, great. If we give it an invalid drive device, it'll say that it can't, that we can't. Well, it's supposed to say that we can't invalid unit, but you get the idea. Nah. Okay. So if we do provide all the right bits and pieces, pass it into DF1. Hopefully you guys can hear the bits and pieces here once I get this all set up. Okay, yeah, we've got sound. Just double checking to make sure that we have sound. I will put in my test disk into DF1 here. There, okay, you see it went, and it went, okay, I don't know what this is. I'm not going to touch it. We're going to get a system request saying that the process will erase the target disk. Okay, no problem. So it starts by issuing a command to the Trackdisk.device called tdformat, which will format the requested track with whatever buffer you happen to give it. In our case, it's all zeros, so we're basically just zeroing out the track. If we were being really correct about this and really wanted to conform perfectly to MFM spec, we would write F6. But I digress. It doesn't really matter on the Amiga at all. And then it will take and write the KickStart image to the floppy. There we go. So now we've written the disk image to the floppy. You've seen it boot and previously in the video here. So now that we've kind of gotten our introduction out of our way that what we're going to be doing, let's go ahead and start writing the piece of software. Of course, I've got MakeKick window open here. It's nice and empty. This is a nice empty work file, and we're going to start from the top. Coincidentally, our make file isn't much different from what we've already been doing in the past. It's pretty much the same here. We need to start by basically specifying our includes that we know that we're going to need. Well, first include that we know we're going to need is exectypes.h. We need that for pretty much everything we're ever going to do on the Amiga. It contains all of our base types that are expected. But to take and shorten things up a bit, we're going to be including all of the exec headers. This exec.h is a header file that simply contains includes to all of the other includes inside exec. The one it doesn't provide, however, is types. So if you don't provide types and you provide exec.h thinking you're going to get everything, you're going to get a whole bunch of compile errors, at least in this ancient version of Lattice C. So, as you saw with the requesters and the sliders and everything else, it is an intuition app. So we need intuition. And because we're drawing things like progress bars, we definitely need the graphics, and we need GFX macros, and we need GFX base. So that pretty much includes all of graphics for us. One thing that we do need that we really haven't used much in previous videos, only obliquely, is we need the DOS library. We need the DOS library because we're going to be opening files inside the file system and reading them. And finally, we need various structures, including the IOTRequest structure or the Trackdisk.device. Those are all the includes that we need. Of course, since we're using graphics, we need GFX, we need a pointer to GFX base, and we need a pointer to intuition base as well. We need to set up some return conveniences so we don't have to cast so much for things like CreatePort. We need CreatePort because we're going to be taking and creating a reply port because we're doing I/O. And we need, since we're going to be making windows, we need open window, and open window is going to pass a pointer to our window structure that we're going to be using. Okay, so what next? Well, we know we need main, and main is going to have some arguments this time, so we need to pass those along with us. The standard Amiga startup, even though we're not using the Lattice C startup, the standard Amiga C startup will take the arguments from the command line and pass them in C calling convention, which means we need an argument count and we need a pointer into each string of the argument themselves in argv. And argc is an int. Argv is an array, is a pointer to an array, to a pointer to a set of pointers of character arrays. So there we go. We have our main, and our main is basically going to have a few things that we know that we're going to do. We need to do some initialization. If init, okay, great. Sure, okay, great. Regardless of which, we need to call done to make sure everything is cleaned up, sure, no problem, and we need to return something. Okay, return 0. Okay, all fine. Let's take and structure these out a bit. Init. As always, anytime you do any calls to Amiga libraries, you need a pointer to their base. So you go ahead and use the open library call to get it. We are not going to specify a minimum version here because we're not using anything particularly new or interesting here. So 0 is fine. If we don't get it for some reason, we return false and the whole program just stops. Same thing with IntuiTexts. There we go. And again, you'll see a lot of this just defensive programming in early GUI programming for sure. Because if you don't do these things, if you just take and do an open library call and it doesn't work for some reason, and you just assume that it's okay, it's going to crash. And in fact, that is the default behavior of just about everything in the Amiga library. If something doesn't happen, it assumes that everything's okay, it will quietly return back, and you will try to use it, and the system will crash. So yeah, you need to program defensively. Finally, we need done, and done is essentially going to do the opposite of what we just did in init. If GFX base exists, then we close it. Same thing for IntuiTexts. If we have IntuiTexts, then we've opened it, then we need to close it. Same thing, make sure that's it. Yep, okay. So that's pretty much it. So we've got init and we've got done. Let's take and do just a quick little bit of sanity here. Finally, if everything is okay, then we call the main program itself. How do we call the main program? Well, let's do a little bit of argument checking just to make sure that everything is okay. Well, if we have less than 3 total arguments, keeping in mind that argv0 is the name of the program, then we call show usage. Otherwise, we give the 2 arguments that we passed in. Make sense? Okay, good. I'm glad you're coming with me on that. So that also means that we need to do a MakeKick as well. I guess I'll put those up here. MakeKick. And MakeKick needs to contain 2 arguments. Essentially, our file name and our derived string. These are both strings here. Okay, finally, we'll go ahead and return through. Fine. We'll do that for now. And just for some basic sanity, we also need show usage. How are we going to implement show usage? Well, we're going to use the AutoRequest function as part of that's part of Intuition to take and draw a simple little usage message here. And it is entirely structured like this. AutoRequest contains the following parameters. The first one is the screen that we want to attach to if it's not the workbench screen. Well, it is in our case, so we want it here. We need to take and show our usage text. This is not a C string, but it is an IntuiText structure, which we'll fill out in just a moment. Few things that we don't need, but we also need our button text, which is going to be essentially our OK button. Finally, the width and the height of our AutoRequest structure. Now, we'll take and do a little sidestep here. Sure, why not? Make a new little window right here, and I will show Amiga lib AutoRequest. What is AutoRequest? This automatically builds a this automatically builds a requester for you here. You need to pass it a window, the text that you want to display. Then there are positive and negative texts for your button here. The positive text goes on the left, the positive button goes on the left-hand side of the requester, and the negative one goes on the right-hand side of the requester. Meh. Then you have some flags which you don't absolutely need to take and fill in, but they're here to set various different features. These are basically for IDCMP so that you can attach custom events that you can track for your requester. Meh, we don't really need them. Finally, the width and the height. So there we go. What does our usage and button text look like? Well, it's pretty easy. All we really have to do, I'm going to take and go to usage text here. And IntuiTexts are like every other data structure in Intuition. It is essentially a linked list. They really like their linked lists. Struct, IntuiText, usage text. And it is comprised of the following. Top offsets here. So let's see. You can see kind of where this winds up here. Let's say IntuiText. So you have, these are the pin number. Let's see. So you have the pin numbers for rendering here. In this case, we're just going to be using the background color here because the requester is going to be white by default. The draw mode that we're going to be using is Jam1, which means just draw the foreground pixels in place. Then left edge, then the top edge, any text attributes that we want to attach, such as a text font that we want to override with, the text that we want to do, and then a link to the next text structure. Okay? So, all right, 00, Jam1. We want to put this at 15.5. This is relative to the top edge of the requester itself. We don't need that, so here we go. Usage text is you can put whatever you want in here. It's treated as a null terminated text, as a null terminated string, just like in C. And then we're going to take and go ahead and add a pointer to our next IntuiText structure, which we'll put right above here so that the compiler will have it defined. Usage text 2, much the same thing. Jam 1, 15, and a little bit, and scoot it down a little bit further. ROM file must be 256 KB in size. Usage text 3. Yes, there's one more line of text. Can you do these as arrays? Yes, you can. So, text 3. There we go. And finally, since there are no more IntuiText structures to render for this particular block, last one is null. So that's it, bam. Those are our IntuiText structures. And with everything here, we should have enough to take and run our first compile. Okay, so we'll do that, and we will go to our CLI. Bam, open up our CLI, trusty CLI that we've used many times before. Workspace, and we'll go to tdisk, where I have our little work directory here. And we execute make. Hopefully I haven't introduced any typos, but given my luck for this particular thing the first time, that never happens. Button text intuition intuition base. Okay, so button text. Oh, I need one for button text first of all. Okay, that's easy enough. We do need one for button text. And there's nothing special here. This is going to be rendered relative. The button is going to take and position it, so there is no special button considerations that we have to make here. So we'll just gently take and scoot it out a little bit. Actually, sorry, yes, there is a tiny bit. Button text, we'll see here in just a second. Same thing before, 00, jam 1, 6.3, and that's where it's going to go. Null, okay, and null. It doesn't have any other text structures attached to it. Okay, great. And so hold on, where's the other one here? That's at line 80. Intuition base, intuition base, intuition library. Intuition base, intuition base. What happened? Intuition. Intuition. You bastard. Intuition base. All right. Intuition. Yes, spelling is important, fellas. Yeah. Let's try this again. Okay. No compiler errors this time. All good. We're not doing all that much yet. You can see our module sizes are modest. They're not even, they're less than 206 bytes each. The total size of the program is going to be maybe 1,200 bytes. Yeah, 1,400. Okay. So now we can take and run it and just not provide anything to see if our requester comes up. Yes, it does. And in fact, yes, it does. But our size is incorrect. And you'll see something rather interesting here with how AutoRequest actually works. AutoRequest will render the positive and negative buttons basically right aligned at the lowest point with a little bit of margin above here. So you can see right here, make file, wrong. So the OK button has been wedged over here onto the right-hand side so that it's usable. And I think I realized where I went wrong. I was seeing 337 here because we're going to be using that dimension for some of the others. Let's just go ahead. We'll fix it and then move on so that the next cell, but we'll test it the next time when we move on here. Yep, have the right size. So it needs to be 320 by 88. We'll go ahead and save that, and we'll go ahead and move on to the next part of what we need to handle here. The next thing we need to handle is opening up our ROM file and making sure that we can open up our ROM file. And that'll be the first thing that we do in MakeKick here. Let's go ahead and start. In order to do that, we need to open up our trusty AmigaDOS programming guide here. Go into my Amiga manuals, and we will go into AmigaDOS, the developer's manual. And this is the original developer's manual, which contains all the function prototypes and everything for everything that we kind of need here. And it has all sorts of stuff, such as creating processes, reading and writing files, etc. And what we're interested in is the open call. Open has two parameters here. The name of the file that we want to open, its full path, and the access mode. And the access mode is described here as either mode open old file, which means the file should already exist and fail if it doesn't, or open new or mode new file, which means create the file if it doesn't already exist. And what we get back is essentially a file descriptor. We'll call it a file descriptor. It's a file handle here, same thing. You can use this to open any file or AmigaDOS device that the system knows about. So not only can you use it to open files, you can use it to open things like con, raw, nil, etc., as you can see right here. So let's use it. All we need to use it is a file descriptor. And that file descriptor comes back from open, fn, mode old file. Cool, right? Okay. Now, if we don't get a file descriptor back for some reason, then we should show some error indicating that that happened. And for that, we'll make another function to do that. Couldn't open ROM text, and then we'll do what we call go to bail. Go to bail, we're using this particular pattern here of using go to. Some people say go to is harmful, but in this case, it's going to give us the ability to take and go down to past the rest of the logic and not have to bump through the rest of the logic or have to define the logic recursively to take and deal with a whole bunch of things that need to happen dependency-wise in sequence. Bail is defined with a label down here, and bail needs to, first and foremost, if we have a file descriptor, we need to close it. So if we open it If we open it, we need to close it, and so on, and so on, and so on. Okay, great. But we haven't defined show error yet. Well, show error is easy enough to implement, so we'll go ahead and just do it. Show error is defined as such. Remember show usage? Well, guess what? It's pretty much the same. In fact, you can just take and collapse these two together. But I got lazy here. Oops. So show error, struct IntuiText. That's what T is right there. Bam. Okay. AutoRequest. Null. T. Button text, because it's all going to be just okay at this point. We can use the same okay text from before. No negative or anything else. And they're all going to be the same size. That's it. That's all we gotta do right there. That's show error. So let's go ahead and build that and work through that. Here we go. Okay. Save that. Execute, make. Here we go. And yes, I'm taking you through all of these processes here. This is going to be a long video, and it's a good reason why I take and make indexes for all of these various things here. Oh, couldn't open ROM text. I actually have to implement that, don't I? Durr. Yes, we're going to be making a lot of these IntuiText structures. We'll take and copy this guy here. That's basically it. Now, this is all pretty much the same thing. The difference here is that the text position is going to be ever so slightly different. Not 6.3, but we're going to use 8.8 here. This has already been proven ahead of time to be very nice for this particular type of window. So save that and we go again. This particular video is going to be real fun to take and go through an index after I've created it here. It's a good thing I have my trusty coffee, and now that I finished my trusty coffee, I can start on my trusty energy drink. Yes, that is the sound of clarity. Okay, build it, link it, we're good. Okay, so now we can start doing things. Of course, MakeKick as before gives us this. Give it here, and oh wow, what happened? Oops, did I make a mistake? I think not enough memory. Oops. Wow. So we had a leak from earlier. I'm wondering if it's going to do the same thing again. Let's find out. Oh boy, let's see if this happens again. Oh, I opened the wrong thing. Okay, blah. It happens, guys. This is a machine without any memory protection, so yeah, stuff like this happens. Workspace, so disk. Let's try that again. Well, that's certainly interesting. Okay, so let me see. I am actually going to do one of my rarefied cuts here to see what could possibly be happening, and we will come back. All right, found the problem. Oops. Again, no function prototypes, therefore no checking of function parameters. It turned out this line was missing. There was one parameter too few here, and this was going on in here, which was causing it to go off into the weeds. Let's fix that here, and now let's continue on. Whee! That's why they invented function prototypes for ASCII, fellas. So basically, the compiler didn't know that that function was incorrectly defined. Therefore, it just went, oh, okay, I'm just going to pass those parameters along, put them in their registers where they need to go, and that's the end of it, right? No, no, not really. And in point of fact, it's kind of interesting. The versions of Lattice before version 4, all of the implementations of functions inside Amiga lib are actually shim functions. That is, they take their parameters in, and then they jigger them into the appropriate, they have a little piece of code that jiggers them into the appropriate registers and then calls the function. This was optimized in Lattice version 4, basically to have the compiler understand exactly which registers each of those parameters would go into, and thus the function calls become direct. And it actually improved performance quite significantly in some cases. So, let's try that again. MakeKick, doesn't know. Okay, fine. Groovy. And if we now take and do foo.cdf1, we see couldn't open ROM file. Okay, great. So now we're starting to see the basis of our program here. So we've opened our file. What next? Now we need to actually do a bit of sanity checking for the destination drive that we're going to be writing to, dfx here. And the x in this case, 0, 1, 2, or 3, actually corresponds to the unit number that we're going to be using as a call to OpenDevice for Trackdisk.device to take and talk to the correct floppy disk unit. So it's in our best interest to make sure that this works as expected. For that, all we really need to do come down here, I didn't make it. Come down here and we'll define another variable here called unit. And we will grab the unit from the second character in df. This is going to be an ASCII number. So if we take and subtract ASCII 0 from that number, we're actually going to get the unit number in binary here, in our, in integer form. Great, nice little shortcut there. If FD, we weren't able to open it, we do another call check here. If unit is less than 0 or unit is greater than 3, then we take and do another show error right here. Invalid unit number. And we go to bail. There's nothing particularly special here because we haven't opened anything yet, so there's no cleanup that we need to do in this case. So that's fine. The really thing that we need to do here is we need to make another IntuiText structure to take and give our invalid unit number text. Invalid unit number text. Okay, great. So what next? Now we can actually start, now that we have our file and we have our file descriptor and we have our unit number for the drive that we're going to be talking to, now we can actually start opening up the drive and communicating. Since we're talking to an Amiga device with a .device file, we're talking to a device driver of sorts, and it works the same way as all the rest of the device drivers in the system. We need to set up exactly the same conventions as we've done for other devices in the past. Particularly, we need a message port as our reply port for the device to send messages back to us if we're interested in them, but we still need to implement it nonetheless. And we need an extended I/O structure specifically for the Trackdisk device. This is defined as IOTDReq, and this is our disk request. This is our disk I/O request that we're going to have. Okay? These two are currently set to null, and we will actually take and start implementing them right here. The first thing that we have to do, we need to create a port. This is a private port for us. Nobody needs to talk to it. So both of these values, both the name that you would normally put here is null, and the priority that we put, this is doesn't have any special priority, so that's also 0. If we don't have a port for whatever reason, then we show an error that we couldn't create the port. We're going to be doing a lot of this. So couldn't open port text. Okay, great. Let's go ahead and make and drop it in here. Couldn't open reply port. Okay, great. So now that we have that, okay, fine. If we don't have it, go to bail. But since we've taken and done a CreatePort here, we also, of course, have to come down here and delete our message port when we're done with it. Okay? So now we've got a port. Assuming that we have our port, we can then turn around and create our disk request structure that we're going to use as our message. This is our message that we're creating so that we can send disk commands down the device port here. So here we go. I/O requests are kind of special because they contain both the destination port for the device that you're talking to, and they also carry the information that the device needs for the reply port to send the message back. So, disk request, struct. Pointing to IO extract EXTTD here, CreateExtIO. CreateExtIO, and since this is an extended I/O request that we're creating, we give it our reply port, and we have to give it the size of our structure here because this can be used for a variety of different devices, each which can have their own custom data structures. The thing that they all have in common is that they all have a standard IO request structure at the beginning of their data structure. So, IOEXT-TD. If we don't have our disk request, can we show error again? Couldn't create disk request. And we go to bail. Conversely, if we have a disk request, we need to close it. Or delete it, that is. Excuse me. Two parameters here. The disk request itself and the size of, so that it can take and free that memory. It passes all of this information in once it's set all the flags and let everybody know that this is now shut down. It calls free mem to reclaim so that it gets that memory back. CreateExtIO calls alloc mem. DeleteExtIO calls free mem. So, okay, there we go. Now we need another IntuiText. Couldn't open port, couldn't create disk request. Couldn't create disk request. Make sure that's right. Couldn't create disk request text. Yep. Okay. All right, fine. So that's good there. That's all there. We're just we're having to program defensively, because if we don't, you've seen it here already with just me making small mistakes here, like functions not being past the correct parameters, system crash, go boom. So there we go. Disk rec. Okay. Now that we've created our reply port, now that we've created our disk request, which contains, among other things, the reply port that the request is going to come back to, now we can actually open our device. For that, we call OpenDevice. OpenDevice gives us either a 0 on success, it gives us a 0 on failure, or it gives us a number containing basically a device handle, which we really don't really need. It's kind of one of those things, whatever, because all the information dealing with our device is actually going to be poured into our disk request packet. So there's a constant in Trackdisk.h called tdname, which corresponds to Trackdisk.device, but I'm going to use the constant here. And the other major thing that we need to pass into OpenDevice is our unit number, which we pulled out above. And we need to pass in our disk request. That's going to be, it's going to link these two together so we can start sending stuff down the pipe. And flags. There are really no usable flags for what we're doing here, so we just set that to 0. Doesn't really matter. If for some reason this fails, if for some reason OpenDevice is 0 on success, otherwise we return an error number. Sorry, yes, thinking too fast. OpenDevice is 0 on success, otherwise we return an error number. Matter of fact, you can kind of see. Apologies. And you'll see I'm using this particular thing here because in this case, this is faster than looking through the PDF viewer, because the PDF viewers that I've been using lately are unbelievably slow. But anyway, so open access. Okay, the error returned back, device name, unit number, IO request that we're going to use, flags. Returns a, there you go. And that gives you an exact deal of what gets passed back as part of your error here. So there you go. If we get this, we're good. If for some reason we get an error, then we say show error. Couldn't open Trackdisk.text, and we go to bail. Now, here's the thing. OpenDevice gives us an error. But we really need a flag to indicate whether or not the device is open. We can reuse the error for this, but I'm going to take and make a flag for this. Device opened equals false. Okay, set that to false. So at this point, device opened is false, because just as we did right here with OpenDevice, we also need to close the device. If I take and just do close device and the device is not open, yes, you guessed it, the machine will crash. Seeing a pattern here? So now, okay, disk request, close device, disk request. Okay, if it's open, we take and we close it. So now we've opened it, we can close it. We good so far? Okay, great. So now we've opened the device and we've got a closed device here. At this point, we have everything opened, so now we can use it. So now I'm going to make a little function called are you sure? And if we say no, we go to bail. The reasons for this have to do with the fact that I'm reversing what the positive and negative buttons are here, because I actually want the positive action to be on the right-hand side. That's just me. But anyway, are you sure? Go to bail. Fine, let's come back up here and let's implement are you sure? Are you sure? And are you sure is actually going to return. The nice thing about it, if you look at AutoRequest like we did before, you'll see that AutoRequest returns either a true or a false, depending on whether the positive or negative button is pressed. So all we really have to do in this case is just return AutoRequest. Bang, bang, boom. Robert's your father's brother. So let's make sure that we put all the right parameters in this time. Are you sure text? Cancel text. We're actually going to be using cancel this time. That's the negative text. And then button text. Sure. No IDC and P flags that we need, and we want it to be 360 by 54 in dimensions. Okay, there we go. So that's our are you sure function right here. So we need to add a couple things here. So we need to add are you sure, and we need to add cancel. Here we go. We'll go ahead and add the cancel text here and base it off the OK text. Cancel text. Okay. Cancel. Boom. That's all we got to do for that. Now I'm going to go ahead and do the same thing here, and are you sure text? And are you sure is going to be implemented like this. This process will erase the target disk. Oh no! Like that. Nice little warning right here, but that's what we need to do. Okay, great. Bang. And we'll go ahead. Are you sure? Are you sure? Come on. Are you sure? Go to bail. Otherwise, we'll go ahead and just to show that we're going to go through, we'll display beep on a success here. Let's see where we are at this particular point in time. We are now at the 118 mark. So save that. Hopefully I didn't make, we did a lot of boilerplate there. Hopefully I didn't make any mistakes. Famous last words, I know. And yes, we've had to do a whole lot to make this work. Oh, I didn't make the couldn't open Trackdisk text. Oops. And it looks like I need to. Couldn't open Trackdisk.device. Couldn't open device open. Couldn't open Trackdisk. Okay, fine. But I also need to make sure. That's 199. So we need to make sure. See, size up. This is where I messed up right here. This is not a, if it were a type def as this, we could do this, but it's not. You have to explicitly define set structures here. So there's no type def here, so we have to say struct IOEXTTD, struct IOEXTTD, like we see here. We'll go again. Like I said, this is going to be a fun one to take an index because it's going to have a lot of weird little fits and starts. The 87th compile. I'm going to have to, as soon as I finish this video right here, I'm going to have to go out, do my morning run, then take and jump in the shower because we have Thanksgiving dinner today. So, yay. Yes, this is being recorded Thanksgiving morning. So now that we're actually opening things up and getting things ready, I'm actually going to be using real file names from this point forward. Okay? So we start MakeKick. We know the rest of this works, so I'm just going to say kick B27.3 ROM, and I'm going to put it on PF1. At which point we get our little requester here saying, yes, this process will erase the target disk. Are we absolutely sure? If we hit cancel, no, okay, fine. If we hit OK, the screen should flash. Bing, there we go. We're good. Okay, so far our logic is going great here. Now, we can actually start doing some interesting shit. And for this, I'm actually going to get out of this particular function right here, and we're going to actually we're going to do our real work. The two functions that will actually do our real work. And the first one we're going to implement is format. The next one we're going to implement after that is write. So now that I could, if format disk, and all we need for this is just a disk rec. If format disk is okay, then we take and write the kickstart. Otherwise, it'll fall through to bail. And there's the main flow of our program. WriteKick needs two parameters. We need the file descriptor that we've opened over here, and we also need the disk rec because we're going to be talking to the disk driver. There you go. So now we can come up here and start filling out our two main functions which do the lion's share of the work. I wanted to get these outside of this flow into their own function so you can see what's actually happened once everything gets opened and you're ready to actually do some work. Format disk needs disk rec. And WriteKick needs both the file descriptor and the disk rec. The file descriptor is simply just the int passed in through open. And like I said before, disk rec, the pointer to the disk structure. There we go. At which point, okay, fine, we return, fine, we'll do that. Okay. Return true, sure, and return. And this right here, same thing. So how do we format a disk? That's actually pretty cool. Now we can actually start talking about how the IO requests actually function here. So what do we need in order for this to function? Well, I'm going to take and actually put a window up so that we can actually see something happening while the format is happening, right? Yeah, why not? It's, you know, we have intuition here. We might as well freaking use it to do something nice and neat while it's doing stuff, because it takes a minute to format a disk, doesn't it? So, fine. We need a window. Okay. We also need a current track number. And we also need a buffer. And if you read through, of course, the RKM does have a whole section on the Trackdisk.device showing how to use the Trackdisk.device, giving you a whole bunch of example information on the Trackdisk.device. And one of the functions that we're going to be using here is TD format. And the thing that it says right here is that TD format really only has one meaningful thing, and that two meaningful things, and that is the well, three things. The offset, which is where we're going to format. The length, which is the length of your buffer, which must be in units of track length. That is number of sectors times TD sector. A little bit about the Amiga disk format. Floppy disks, like all disks in the system, are divided into units called sectors. The sector size on an Amiga is 512 bytes. And for each track on an Amiga floppy, there are 11 sectors. And these all correspond to constants that are in Trackdisk.x. So you see numsecs, that's 11, TD sector, that's 512. So the buffer that we need for format, it's going to take and send the contents of that buffer. It needs to be at least numsecs times TD sector. And then it will take and format the requested tracks, putting in all the address markings and everything for us, and in the correct format with the correct sector gaps, the correct address marks, all that nifty stuff. But it will do us a solid by filling each sector with the contents of whatever we put in the IO data field. It's very nice. It says you should do a read pass to verify the data. We're not gonna. You basically just, after you do a format, you do a TD read and a command read, and then read back and compare it with the buffer. Meh, whatever. We don't have to do that, but they suggest that you should because it's a floppy. Whatever. So, with that, we need a buffer, first and foremost, for our data, right? So that buffer is going to hold our blank sector. It only needs to live for the life of this function, so we can put this in the stack quite easily. Oh, sorry, so we can put this right here, and we can put a pointer in the stack, and when we're done with it, we can free it. So this data also has to be aligned on a word boundary. Good thing, AllecMem will take care of this for us. So as it said before, TD sector times numsecs, and this needs to come from anything that you pass to the Trackdisk device. Needs to come from chip memory. That's because Paula is blitting. That's because Paula is blitting that data directly out, DMA directly out from chip memory. Now, I say this here in the context of version 1 of the operating system software. In version 2, Randall Jessup rewrote the Trackdisk device. So that data could come not only from chip memory, but from any public memory that is either chip or fast memory. But since we're using 1.0 here, we're just going to say, okay, this is going to come from chip memory. And we're going to make sure that this comes from chip memory by setting a flag. And we're going to go ahead and clear it as well, just to be nice about it. If for some reason we don't have a buffer, we run out of memory, we show another error. No mem for format. And we do another here. Format by. So again, it's because we did an AllecMem here. If buff freemem and freemem buff and TD sector times numsecs. Now this is kind of interesting because freemem on other systems like Unix, whatnot, you just pass it the pointer, it will take care of it. But with freemem, you also have to pass in the length of whatever you happen to allocate. An interesting little peculiarity there. And at some point, I'll take and dig into why that's the case. So no mem per format. All right, fine. Another IntuiText. We're going to be doing a lot of these. grab this guy right here, and we'll just duplicate it. Hold on. No mem for format. Okay, great. Fine, fine, fine. Get back into the neighborhood here. Okay, so fine. If we have our same little thing here. So we have a buffer. Okay, fine. Allocate it. If we can allocate it, great. If we can't, fine. So now that we have our buffer, what's next? The next thing that we absolutely have to do, we have to turn the motor on. And yes, this is our responsibility. We need to do this. Good thing, but this will be our first command to the Trackdisk device. So we fill out our disk request. And if you want to see what this actually is, I said, go ahead and look at Trackdisk.h. And you can see the data structures for each of these. Let me see if I can actually pull this up here. Let's see if I can. Trackdisk. Oh yeah, here we go. Oop, that'll work. We have, of course, all of our little constants that we have here. Yes, these are obsolete because in version 2 you have a command to get your disk geometry. We don't have that in version 1. We don't need that here, so we just use the constants. So all of our commands that we can send, everything else, but we have our IOTDReq. And just like every other data structure that builds on other data structures inside AmigaDOS, you take and tack on your special stuff onto the end of your data structure. So the beginning of this data structure is actually a standard request right here that you fill out with IOTDReq. And of course, IOTDReq, if you look at IO standard command, you can actually take and go, okay, let's see if I can do that. IO standard request, create standard, and in fact, we could actually implement this using just standard IO requests. It's all up to, we're not using any special commands here, so we could actually do this. But if we look at IO standard, the IO request, we can see that we have device and unit, and we've got our message structure here. All of this gets pre-filled out, but we have our device command, we have any flags that we need to send, and error, that sort of thing. IO standard request, flags, error, actual. But we also have a length to the requested number of bytes that we need to transfer. We have our data pointer, which we're going to deal with, and we have our offset. And this offset is actually going to be used by Trackdisk here to take and position ourselves on the correct track. But I digress. Anyway, just wanted to kind of put this all in context here. So IO command, we need to turn on the motor. Turn on the motor. Then the interesting thing about the motor command, it gets its flag for whether you want to turn it on or off from the length, which is very funny. So length equals 1 means on, length equals 0 means off. And finally, we do IO, we do a disk rack. Okay? So at this point, the motor is on. This means that at the bottom here, at our buy, we need to make sure that we need to turn our motor off. Oh, come on. So there we go. There's our DIO, disk rec. Okay, motor's on. And at this point, now we can basically say, okay, great. Now we can start setting up our format request. We're going to use the same request here because by the time DIO finishes, it's going to wait for the DIO request to complete. And in the meantime, other tasks that need to run will preempt and do their thing while this thing does its thing. So everything can multitask. Fine. Once it's done, it comes back. We can reuse the disk request. And we want to set up for a TD format. This will say we want to do a format command. IO length, which is TD sector times num sex up above. Yes, you could implement that as a constant, but I really wanted to take and echo this across so you can see how these things fill out. IO length, and then finally IO data. It's all going to be the same data, no matter what. This is going to be just a pointer to a buffer, and since this structure actually has it set up as an A pointer, as a standard Amiga pointer, C style pointer, that is exactly the type I'm going to use here, so the compiler is happy. So, set that up. We're not ready yet. We just set those things up because we're going to be adjusting the offset value in a loop here. But before we do that, we need to open up a window. Open window. And we're going to open up a window for our format. What's NW format? Well, if you've seen what I've done with Intuition in the past, you know that we're going to make a little new window structure here. Let's go ahead and build this sucker. Give me a moment. Put it in view so I can see it. Yep, struct new window. Here we go. NW format. Okay. So this is going to be a window running on our workbench. We're going to put it at the top left portion of the screen. It's going to be 180 by 32 in width and height. We're going to use we're going to use block pen 0 and detail pen 1. Null here, don't need it. We don't need to grab any events or anything. We're going to set some window flags. We're going to say that this is a draggable window. It has depth gadgets, and we want it to activate when we see it the first time. Oops. Yep. Activate. So, furthermore, some more parameters we don't need. And we're going to give it a title. We're going to put the informative information in the title. Formatting. Okay. And again, more info. We don't need gadgets and things that we're not going to put in here. And 320, 180. Okay, fine. These things have to be there. We're just going to put them there. And since this is a workbench window, it's not a custom screen, but we're going to do work wbench screen. So there's our window. Yay. Great. We're going to open our window. Well, what happens if we can't open it? If it's null for some reason, then we got to do the same thing we've done for everything else. Can't open window. Oh my gosh. Yes, there's a lot of this. A lot of this in GUI programming. You just buck up and deal with it. Couldn't open format window. Go to format by. Okay, oops. And because we did this. Literally because we did this. Now we have to take and do this. If If we have a window, then we close it. See? Okay. Couldn't open format window. Okay, great. It's another one of these show errors, so I'm just going to take and grab same text. Big whoop. Okay, so now got that. But at this point, now we can actually start doing some interesting stuff here. We'll go ahead and set up a couple of little things now that we've got a window that we can deal with. I'm going to set an outline pen, and we're going to make it black. We're gonna make it white, actually, and we're gonna set an A pen, and we're gonna make it white. Okay? Then we're gonna take and draw the background of our progress bar. So again, rect fill, pretty much simple. You got a raster port here. Then your the top left and the top and the left of your rectangle, and the bottom and the right of your rectangle. Yay! Riveting. And at this point, now that we've drawn that, now I'm going to take and change and reverse these, because we're going to draw in exactly the opposite way. Bam, bam. Okay, so now we've set those, got them ready to go. And now we start iterating through our tracks. For track equals 0, and track is less than numtracks. Track plus plus. Bang, bang, boom, boom, bickety. Okay. We're going to start by basically doing a rect fill to update our progress bar. Starting at 816, track plus 8, and because we're actually scooting over by 8 a little bit. And there we go. World's quickest progress bar here. It's 160 pixels across, and we have 160 tracks. So as it does each one, it will take and draw the next bit of the rectangle. Yay! Great, groovy. Finally, we do the part that actually does the magic here. We set the IO offset for where this is going to go. Now, what is this? If you actually take a look at IO offset for the Trackdisk.device, it basically, you give it a byte number, and that byte number should always be in 512 byte instruments. So the first track is is 0 through 5632 is the first track, and so on and so on and so on. So you're giving an absolute position, an absolute byte position that's multiplied out, which corresponds to the track that you're going to be outputting. And because of the way that the Trackdisk.device works, it tells you very matter-of-factly that any reads or writes to the Trackdisk.device need to happen with an offset that is divisible by the sectors. All of this is described here on page in the first pages of the Trackdisk.device, right here. It's all pretty much described all right here. So we're basically just saying, okay, now you're going to format the next track. And then because we're dealing with format here and the buffer is track sized, we're scooting things forward a byte value, 5,632 bytes for each track going forward, which will cause Trackdisk to move the head up. There you go. Finally, we do IOTDReq, and this formats the disk. Finally, at which case we're okay, we're good. We can kind of do this. All right, groovy, at which point we are done. We're done. That's our format routine. Let's see if this works, and let's test to make sure that this actually works. First, we're going to take and compile this, and while this is compiling, hopefully there's not going to be any errors. If there are, we'll take and fix them, of course, like we always do. And I'm going to go eject this test disk right here. And we're going to go over here for just a moment. And we're going to make our test disk. This is my vintage Commodore Amiga disk directory. It's got all sorts of crap in here. But the thing we're going to do is we're going to make a little test disk. And we're going to fill it with garbage. An Amiga disk is exactly 901,120 bytes long. And hey, we have no errors. We're doing good. Well, let's take a look at this and see what we actually have here. We've got a whole bunch of just random bullshit here. Okay, fine, great. Matter of fact, let's do this again. I'm going to make sure that we really get, because I want this to be garbage. There we go. You can, or not, like, is it, oh, I'm guessing it's because something has hold of it. Hold on a second, screw this shit. Come here, I'm gonna make another one here. What is going on? Oh dear God. Really? Really, man? Okay. Try that again. All right. Silly. So goddamn silly. Hexedit, TextEdit. All right. Lots of garbage. Just garbage all the way through the file. We're doing this because we're going to be formatting this, and with the format working like it's supposed to, it should make this nice and clean, right? Let's see. MakeKick. We're going to attach this disk. It's going to complain about this disk and say it's not a proper disk at all. Oh, that's what happened. I had a typo. Yeah, typos will just ruin your day. We can see, yeah, it's just a mess. It's an absolute mess of a disk, but that's fine. If everything goes as it should, we should be formatting this disk. Let's see. Drive motor comes on. Oh, there we go. We are formatting. There we go. Okay, motor turns off. We're good. We can see that the motor's turned off now. And now if we actually take a look at this disk, oh my gosh, look at that. Nice and crispy clean. And we can scroll down, you know, let it go for a bit, and we can see that it has absolutely wiped this disk completely clean. And on a real drive, you would have this, plus the fact that you would have proper address marks on the disk. So it's now a valid disk. There's just no file system on it whatsoever. So you can't just turn around and use it. Oop, looks like I need to add one more track, but that's fine. It won't matter. Yeah. We'll go ahead and add one more track. Track number tracks plus one. Okay. That's cool. There we go. Boom. And that's fine. So there we go. It's written to. We're done. Yay. Now, format's done. Now, how do we take and write the kick? Well, kick is done in a very similar way to format, except instead of using TD format, we're going to use the command write. We're going to use the command write command. Okay, groovy. Write kick. Here we go. So again, car buff equals alloc mem PD sector. We want, we're going to make this simple. We only need just enough buffer to hold a single sector that we're going to read in, 512 bytes, and a sector that we're going to write out. This also needs to come, like it did before, from memf chip. And we want to go ahead and clear it just because. If no buffer, once again, show error. Could not alloc sector. Okay, let's go ahead and put that in. Could not allocate sector. Okay, got that, got that. Come back down here. Okay, great. Furthermore, same pattern. If we have a buffer, then we take and free it. Same thing. Okay, so we have that. We go ahead, as part of this whole process, now that we've got our memory here, let's go ahead and create that mythical first sector so that the Amiga knows that this is a kickstart disk. Funny enough, that's really easy. That's it, folks. That first sector is completely blank, save for the first 4 bytes being K-I-C-K uppercase. Now let's go ahead and open our window. Like we did before, but we need it here too. Struct window, null. Okay, fine. If we don't have it, Couldn't open write window. Go to write by. Couldn't open write window. That's it. Okay. Couldn't open write window. Go to write by. And the same thing. If W, then we close it. Okay, good. So now we've got that window open. It's ready to go. We did kind of the same little shuffle that we did before. Same basic principle. We make a progress bar again. We go ahead and fill that progress bar out, 8, 16, 264. As it happens to be, if you do a little, with the way we're going to be calculating the progress bar, there's going to be 256 possible positions in the progress bar. And if we add 8 to that, that's 264 for the padding. So there you go. 824. Okay, boom. Now we take and do set A pin, set O pin, set A pin, our port 1 and 2. Same thing we did before. Same thing. So we're going to be doing the same trick that we did before. And once again, we call upon our good friend, motor on, motor off, which, if we do, let's just go ahead. All right, we'll cut and paste it here, but the prudent thing to do would literally be to take and put this in its own function and factor it out. This video is long enough already. And again, turn motor off. That's it, same thing. Motor on, motor off. And now we set up the write request. DiskReq, IOTDReq, IO command, CMD, write. We're going to use the standard request. There are extended requests which allow you to get access to certain things like the label fields. We're not going to use them here. The Kickstart disk doesn't need them. So we're just going to use the standard forms of these commands. IO length. Length has to be at least a single sector. You can write more than one sector at a command write. If it's a sequential write, you can write a whole bunch of sectors out, and Trackdisk will happily do that, so long as you provide the appropriate offset, right? IO length, ED sector. We're only going to be writing a single sector at a time for each request here. That's perfectly fine. But if you do write multiple sectors, it happens faster. You just have to have the memory and the buffer set up. You have to have your buffer set up and everything good. So here we go. IO data. Data is going to point to our buffer, our one sector buffer here. And we're going to go ahead and set offset. Because we've been using this, and the format command has just gone to the end of the disk. We actually need to reset offset. we need to go back to the beginning of the disk. And here we go. All right. Now, one variable that we're going to need for all of this is our read length buffer. In this case, L is, I'm going to go ahead and set that to TD sector. It's 512, right? And we're doing this because I've already built, as part of our setup process, the very first sector that we need to write, which is our custom kick sector. So I'm going to go ahead and we're going to do the write first and then read the next block in. That will make this implementation of this loop much simpler. So, while we have some length, while length is greater than 0, we do the following. We figure out what track we're supposed to be on. This is kind of interesting because all this is here for is for the progress bar. So we're going to take and crunch this down because this value is a byte offset on the floppy. And we're going to do a real quick frickin' division here just by shifting it down so that this becomes a value between 0 and 256. So, just really quickly, that's the only purpose that this is actually here for, is for the following rect fill. Look familiar? Okay, great. Finally, we do IO because we've already set everything up above. We go ahead and do the IO for the disk request. And then we go ahead and scoot forward our offset by length, which in this case is 512 bytes in the correct case. That will scoot us to the next sector, right? And then we reset L again by reading from our ROM file. Remember that file descriptor that we opened way back in the main program? Okay, we're going to use it here. We're going to call read to read the next sector from the file, put it into buffer, and we want to have a sector's worth of data. And when it reaches the end of the file, L will be 0, the loop will terminate. Finally, and this is important, we need to flush out everything. Once we have done all of our writes here, because the kickstart doesn't end cleanly on a track boundary, the Trackdisk.device wants very badly to deal with things in terms of tracks. If you don't send out a complete set of tracks here, it's going to wait until you do, or you send an update command. Command update. Again, one of the standard commands shared across all devices here. They really tried, but ultimately, like most other I/O subsystems, they fall into the whole thing of, well, you need IOCTLs for things that don't fit into open, close, read, write, update, that sort of thing. Plan 9 has a very nice way that they dealt with this particular problem, but that's a whole different discussion. So we flush everything out. All we have to do is change the command. Update doesn't pay attention to the rest of the fields in the command, whatever. But this will take and flush anything that's in the track, that's inside of Trackdisk.device's internal buffers, etc., out to the disk and write the whole track out to the disk. Make sure that that's done. Finally, we can fall out. We can fall out because at this point, the BI will turn the motor off. It will close the window. It will free any memory that needs to be freed. And then we're done. That's it, man. Okay, it's been a long road, but we are here. I think we're going to finish this nice at the just shy of the 2-hour mark. So let's go ahead and save this. Let's see if it compiles. Let's see if I didn't make any mistakes here. We'll take and build it. That was a lot to cover, but I hope this gives a good insight into how the Trackdisk device works. There are other things that you can do too. Oh yeah, NW. Excuse me. Let's come back here. I totally forgot to write. NWWrite. Oops. Let's go ahead and fill that out, shall we? Much the same thing, nothing too special here. It's just a slightly bigger window. Same detail pins, everything. No. W bench screen. Okay, great. Boom. There we go. Let's actually make sure that that's in place. And I want to make sure, let's say I've got 199. Let me look at 199 real quick to see if there's a cast I can fix real quick while I'm at it. Because I don't want to see any compiler warnings if I can avoid it. Or not. It doesn't really matter. Yeah, fuck it. Doesn't care. I hope nobody minds if I curse occasionally. Meh. There are other things that you can do as part of housekeeping. For example, you can notify the disk operating system that the disk has changed. We're not doing that here, but that's just more commands that you send through the request to basically take and refresh the disk, that sort of thing. 215. Let's just see. I'll go ahead and take a look at it real quick to see what that was. Oh, okay. It's just that call to ALEC_mem. Big whoop. Okay. And that's just because ALEC_mem can allocate all sorts of different pointers to all sorts of different things. They're void pointers. So. And in Amiga land, pointers are 32 bits, and well, ints are 32 bits. So you can, at least with this compiler, it's relatively, you can use them interchangeably. And the compiler may warn you, but you can pass them back and forth just fine. So there we go. Now with all this, we should be able to write, and we should be able to write our KickStart. Put it in DF1. Okay, there it is. It will erase the target disk. You ready? Formatting the disk. And there we go. We're reading from our ROM file, as you can see from the HD light, and writing out sectors onto the disk. There we go. Let's see what we wrote. Look at that. There's our kickstart with our kickstart header, and right there at the 200 byte at the 200 or 512 byte mark, we have the next sector, which starts our kickstart ROM. And interestingly enough, look here. There's the date stamp for this particular kickstart. It's Tuesday, June 25th, 1985. Notice that that is right there on the cusp of the Amiga launch event. Let's boot this thing and see if it works. For that, we will spin up another copy of WinUAE, because we have all the computing power in the world that we need these days, even in our laptops. It's amazing, isn't it? We'll go ahead, go quick start. I will set this guy up with 512K of chip RAM this time so that GraphiCraft could potentially run. And we will insert our test disk 1 just to see what happens. And in fact, I will remove it from here. Okay, it's removed. There it is. Good, good, good. I'm going to go ahead and flip on the sound here for the built-in drive here, so we can hear it. Normally I have that turned off because I don't want to hear the click, click, click. And even on my real Amiga 1000, I run no click. That click drives me nuts. So here we go. Let's start this goofy thing. I'll just eject and we'll boot. Oh, come on. Don't do that. Oh, come on. Why? Okay. Excuse me. I'm going to do that again, because I need that. I want that to be turned on. It will not. This will not boot correctly if it's not an NTSC, because this is a the PAL machines didn't exist yet. All right, there we go. Looking for the kickstart. Let's see if she boots. Pop in the floppy. Test disk 1. It's reading. Because if it couldn't find that header, it would just bounce right back to that splat. Okay, reset. And there we go. You'll see this because of the beta ROM here. You can see some bits and pieces where it reinitializes all the chip RAM pointers, and you see some garbage there for a moment. So let's put in our GraphiCraft disk. This particular workbench will only work with this particular version of Kickstart here. So at least this way now, the original Amiga 1000s can boot this original Beta KickStart and experience this environment. But now we have a way to take and boot, to make Kickstart disks with our utilities here. And I've shown you how to take and use the Trackdisk.device to take and do these sorts of things. Let's see if Graphic can load. Now that I have enough memory, it should be fine. There we go. There's our GraphicCraft V27 release 06. We'll take and open something. We'll open a painting, sure, why not? There we go. Look at that. Woot! Doing good. Ooh, I got the cursor got on there, so yeah, it got kind of scorched there, but that's fine. There we go. It's doing great. So there we go. I'm going to end the video here. So we've gone through and shown how the Trackdisk device works. We've used the Trackdisk device to take and create a Kickstart disk from a ROM image file, and we've proven that the resulting Kickstart disk will actually boot. So with that, I'm going to end the video here. Until next time, guys, have fun.